characteristic equation. This part is from section 5.0 of text. In the last lecture, we introduced eigenvalue and eigenvectors. So for a given matrix A, say matrix A is given by n matrix, then if some number lambda and some vector u satisfies a u equals lambda u, then this is called eigen pairs, or you can say this is eigen value, and this is called eigen vector corresponding to eigenvalue lambda. So usually the structure of eigenpairs are given, you can think of like this. So suppose you have lambda 1. Suppose you have A equals 3 by 3 matrix, A11, A12, A13, and A21, A22, A23, A31, A32, A33. Then what you can expect in general, but not always, you can expect at most 3 different eigenvalues. But sometimes they may have 2 different eigenvalues. Whenever, for example, lambda 1 equals lambda 2, then you have 2 different eigenvalues. So for each lambda, for each eigenvalue, there are a bunch of eigenvectors. This is called, so a bunch of eigenvectors, this is called eigenspace, corresponding to lambda 1. Of course, for lambda 2, you have a bunch of, here I have to say u is not equal to 0. So eigenspace. So for each eigenvalue we can find eigenspace. So what we can now, in the lecture we covered that, in the last lecture we covered that given a specific eigenvalue, then we can find eigenspace. In other words, we can find all eigenvectors corresponding to lambda. So given eigenvalue lambda for A, then eigenspace is equal to null space of A minus lambda I. So this is how you find it, or you can say, or write solve A minus lambda I x. Then the solution set gives your eigenspace. So now we're going to complete how to find eigenpairs. So the final goal is to find eigenpairs for a given A. For the time being, what we know is if you give me lambda, if you tell me lambda, then I can find u. Actually, all of the u's satisfying corresponding to given lambda. But I don't know how to find this lambda. So today we're going to talk about how to find those lambdas, eigenvalues. So for any n by n matrix A, if there are a non-zero vector x and some scalar lambda such as ax equals lambda x, then lambda is called eigenvalue of A. And we know that lambda could be multiple. The eigenvalue could be multiple. The set of eigenvalues is called spectrum of A. So we may have 2 eigenvalues, then the spectrum is a set of 2 numbers. So how to find the spectrum? In other words, finding spectrum is equivalent to say find all eigenvalues. So Those are equivalent. So lambda is eigenvalue. Or you can equivalent to say a minus lambda ix equals 0 has non-trivial solution. What it means is determinant of a minus lambda I equals 0. So a minus lambda I is singular. So those are all equivalent things. So for the spectrum is the solution set of the characteristic equation determinant a minus lambda I equals 0. So here, this is equation. Left hand side equals right hand side. This is equation. That means there's unknown number, the solution you're looking for. The unknown number is not A, not I. I is identity. A is given matrix, but lambda. So you want to find lambda. So this lambda is what you want to find. This is solution. And if you find this solution, then this gives your spectrum. So here's the strategy, how to find eigenpairs. Two steps. Basically, you first need to find spectrum or eigenvalues, and for each eigenvalue you need to find eigenspace. So how to find eigenpairs for m by m matrix A, first write characteristic equation, determine a minus lambda I equals 0. We will see from example how to solve this kind of problem. So how to solve this equation. So you find lambda from here. In other words, you find eigenvalues. So find all eigenvalues by solving this characteristic equation. And then find eigenspace of each eigenvalue, lambda, by null space of a minus lambda I. In other words, you want to solve a minus lambda ix equals 0 into PVF form. So we are going to look at easiest problem, 2 by 2 matrix. A is squared matrix given by 2 rows, 2 columns, and write characteristic equation. So the characteristic equation is determinant a minus lambda I equals 0. A is given by 1652, 1652. So a minus lambda I, what does it mean? So it means you want to subtract lambda from each diagonal edges. So because I is identity, multiplied by lambda, so diagonal entries becomes lambda, otherwise 0. So this actually tells me you want to do subtraction for each diagonal entries by lambda and then copy the other entries. This is a minus lambda I. And then what is determinant of a minus lambda I? For 2 by 2 matrix, it is just cross multiplication and take the difference. So that gives me lambda squared minus 3 lambda and minus 28. This is, and the equation has to be given by left hand side equals right hand side. So it is equals 0. And from this equation, this is my characteristic equation. This is characteristic equation. So this characteristic equation is nothing but polynomial equation of second order. So in other words, this is quadratic function, and or you can say this is quadratic equation. Now for quadratic equation, we can usually do factorization if possible. And from here, we should find lambda 1. I usually put largest from largest to the lowest, so if you have multiple numbers. So lambda 1 equals 7, lambda 2 equals negative 4. You don't have to order it from the largest to the smallest, but this is convention. So I have 2 eigenvalues. So the answer for second question is spectrum is 7 and negative 4, a set of 2 numbers. So find the spectrum of A. Now find eigenpairs. For eigenpairs, so we have spectrum. Then this is basically the first part. Now, the second step is to find eigenspace. So for 7, I need to find eigenspace. And for -4, eigenspace. So what we need to do is we solve for a given lambda 1 equals 7, solve a minus lambda 1 I x equals 0. So if you look at a is here, and minus lambda 1 means 1 minus 7, 2 minus 7. So a is 1, 2, 6, 5 for the rest. This is a, but for a minus lambda 1 I means take 7 out from each diagonal entries and solve this. So -6, 6, 5, -5, x equals 0. And we can, of course, do the REF. So it becomes 1, -1, 0, 0. Maybe I should do augmented matrix. So the augmented matrix you want to solve is 5, 5, -5, and 0, 0. And this is easy matrix, and REF is given by, after some EROs, you can figure this by yourself. So 1, -1. So from first row, you have x1 minus x2 equals 0. x1 equals x2. Now, x1 is basic variable because this is pivot, and x2 is free variable, so you just copy this itself. And then x is x2, 1, 1. So this is PBF form. Then what is eigenspace? The eigenspace is nothing but, so when we have this PBF form, eigenspace of lambda 1 equals 7 is going to be the span of the vector given in the PBF form. Now, this is first eigenspace. Because we have another lambda, which is lambda 2 equals -4, I need another eigenspace. So lambda 2 equals -4, and a minus lambda 2I x equals 0. This is the equation you want to solve. Or you can say we have 1, 6, 5, 2 as original matrix, and minus -4 for each diagonal entries, and solve this. So then the matrix is given by 5, 6, and augmented matrix, you need to put 0 to the other side, and this is 5, 6, 0, and x. So this case on the augmented matrix, so I just write this here, it is 1, 6 over 5, 0, 0, 0, 0. And from here, x1 is, from first line, if you divide, is so -6 over 5 x2. And x2 is just x2. From now we can write PBF and the eigenspace of lambda 2, which given by -4 is span of -6 over 5, 1. I will put bracket. So this is the end. So we have two eigenspace. This is one eigenspace corresponding to -4. The other one is this corresponding to 7. eigenvalue, so there's one proposition. The eigenvalues of a triangular matrix are entries on its main diagonal. What does it mean? For example, if you have A1, A2, A3, and this triangular matrix means one side is 0, the other side is some numbers. In this case, if a matrix is given by lower diagonal, then the spectrum of A is just A1, A2, A3. So those diagonal entries, main diagonal entries. So the spectrum is A1, A2, A3. We can easily prove that A minus lambda, for the spectrum you want to solve this. What does it mean? It means A1 minus lambda, A2 minus lambda, A3 minus lambda, and this part is 0, this part is some numbers, and take the determinant. And because triangular matrix, its determinant is given by multiplication of those diagonal entries. So you just multiply them together, A1 minus lambda, A2 minus lambda, A3 minus lambda equals 0. So that means to solve for lambda, lambda has to be one of those numbers from here. So lambda 1 is A1, lambda 2 is A2, lambda 3 equals A3. So that proves the proposition. So later, if you observe the given matrix is given by triangular matrix, either upper or lower, then you just take those numbers on the diagonal entries, which gives you spectrum. So here's one problem. Find the spectrum. So the spectrum is 5, 3, 5, 1. Otherwise, if you want to really solve it, it may involve computation, longer computation. So 5, 3, and there are two 5s. So you don't, in the sense, you don't repeat 5. But we call, because 5 appears twice, so this is, we call this as multiplicity of 2, multiplicity of eigenvalue 5 is 2. But these are multiplicity equals 1 because it appears once. Multiplicity 1. All right, this is the end of the lecture.